Hello. In this section, we are going to present the article Towards an Efficient Real-Time Anomaly Detection System for Cloud Datacenters. My name is Ricardo Dias. I am a Master of Computer Science from PUC, Rio, and a database specialist at Global. This research was built with Leopoldo Maurício and Marcos Poggi. Maurício is my co-worker and he is a doctor in engineering. Poggi is my master's advisor and he has a PhD in applied mathematics. Let's check the agenda. We start by the motivation. Then we explain the proposed algorithm and anomaly detection system. We also talk about the framework used in this research. After that, we show the results and conclusion. Data center environments are commonly huge, with thousands of machines and applications. It's dynamic, with constant software and hardware updates. It's also complex, hosting different types of equipment and varied hardware and software configuration. All applications and devices in a data center are monitored because they are often critical. Hardware and software problems, as well as DOS attacks, may cause failure on services. Therefore, we propose to use efficiently anomaly detection system to identify problems in advance. In this paper, we implement a new, accurate, fast, and self-configurable algorithm. Our algorithm efficiently uses memory and does real-time analysis. We call the proposed algorithm as Decreased Anomaly Score by Repeated Sequence, or DARS. We collect machine metrics and build time series to be processed by DARS. The behavior or characteristics of the time series are represented as the data sequence. A new sequence is a new behavior, so DARS recognizes it as an anomaly. Then, we use sequence frequency to compute an anomaly score. The score indicates how anomalous is the observation. A sequence is a subset of consecutive time series elements. The size of the sequence is defined by a parameter. Frequency is the number of times the sequence appears. This number is stored in an internal data structure. Moreover, the raw anomaly score is given by this formula. Here, occurrences represent the frequency. Once the number of different sequences inside a time series can be huge, the processing time could be excessive. To solve this issue, we normalize all input data to create short, fast processed, and memory-saved time series. We normalize time series transforming the input value into an integer between 0 and a normalization factor that we'll choose to call theta. Hence, we limit the number of sequences of a time series without changing its main characteristics, as we can see in these charts. Some time series have unpredictable behavior caused by noise or the random nature of some metrics. In these cases, using the raw score to threshold anomalies would lead to many false positives. To deal with this issue, we create two versions of DARS, DARS rest and DARS likelihood. They use different techniques to compute the final score from the raw score. Let's see the algorithm. The used likelihood input parameter tells which DARS versions we use. Here, we compute the raw anomaly score. In line 25, we compute the DARS rest score. DARS rest is most raw score for a period defined by the rest period parameter. In line 11, we use the anomaly likelihood function to compute the DARS likelihood score. Here, we normalize the input data. and here we store the sequences. Here we count the sequence occurrences. In line 50, DAS returns the final anomaly score for each input. More details about the algorithm are in the article. Let's see how it works through some time series charts. Using theta equals 7 and sequence size equal 2, the original chart becomes the second one with normalized values. Moreover, the third chart illustrates the raw anomaly score calculated by DAS algorithm. Here we have the final anomaly score chart computed by DAS REST. And now the final anomaly score chart computed by DAS likelihood. This table represents the algorithm step-by-step implementation. The dataset is the same used with the time series shown in the previous slides. For each input, it shows the normalized value, the sequence, the number of sequence occurrences, the raw score, the rest score, and the likelihood score. Now, we'd like to present the proposed anomaly system we built. It uses the algorithm we've just seen. The system's name is Sophia Anomaly Detection. This picture illustrates Sophia Anomaly Detection System. We have developed a collector, a processing, and a visualization modeling using open source tools. We use Telegraph and Kafka to build the collector model. We install the Telegraph agent on each monitored machine to get metrics such as CPU, memory, and networking. The Telegraph agent sends collected metrics to Kafka to be later consumed by other applications. The processing model analyzes metrics, instantiates the anomaly detection algorithm, in this case DARS, and sends the anomaly scores and alarms to the visualization model. DAS algorithm generates an anomaly score for each observation in time series analyzed. Then, the system compares the anomaly score with a threshold to decide whether to generate an anomaly alarm or not. Sophia's anomaly detection system generates anomaly alarms on ZABX and sends anomaly score to timescale in visualization module. The user can also see anomaly score charts through Grafana. We use an open source framework to evaluate DARS. Its name is Numeta Anomaly Benchmark, or NAB. The NAB framework executes each algorithm to process a dataset and generate a score in order to indicate how well they are. This scoreboard is published on NAB repository and illustrates some of the state-of-the-art anomaly detection algorithms evaluated by NAB. Now let's see the results from DAS and Sophia system. This table shows the scores calculated by NAB framework. Here we use the internal NAB dataset. DAS likelihood is the best in this scenario, achieving the score of 70.3 on standard profile. On the other hand, using the Yahoo dataset, DAS REST achieves the best results. For the runtime scoreboard, we measure the time each algorithm takes to process an entire dataset. DAS REST is the fastest to process the NAB dataset. It takes on average 23.6 seconds. When you use the Yahoo dataset, both DAS are in the first places. I'd like to point out that, except for DAS, the algorithms that had performed well on punctuation had poor results on runtime. We also evaluate the amount of memory used by each algorithm to process a time series with 10,000 observations. The figure shows that both DARs use less than 1 megabyte of memory. They use less memory than any other. Now, let's see some results from Sophia's system. We implement the Sophia system in Globus data center. We install the telegraph agent in 2800 machines to collect 5 different metrics, with a 1-minute collection interval. The table shows the number of observations analyzed and anomalies detected by the system in the period of 10 days. The process time of each metric was nearly 1 millisecond. The anomaly score is available in visualization modeling in less than 1 minute after it is collected. The system is able to analyze 20 million observations per day without any delay. This paper proposes two anomaly detection algorithms, DAS-REST and DAS-likelihood. Both had excellent punctuation results, being among the first in all analyzed scenarios. They are also faster and use memory better. We also propose and implement the Sophia anomaly detection system that collects and analyzes metrics in real time on the Globus Cloud Datacenter. Due to the better overall results, we decided to use DAS-REST on Sophia. Sophia, using DAS-REST, provides an accurate anomaly detection service. The proposed algorithm and anomaly detection system are available on GitHub. Thank you for listening. Now we are available for questions.